log B over A is 2.8. So B over A is.
Back to the other page for a second.
Okay. An empty parallel plate capacitor has a capacitance of 20 microfarads. How much charge must leak off its plates before the voltage across them is reduced by 100 volts? Okay, so C is Q over V. Okay, so this was the initial charge and initial voltage, and final charge is initial minus and let's say this much charge leaks out, and the voltage is initial voltage minus 100 volts, and the capacitance remains the same. So this is equal to Q initial would be so Q initial. Oh, that do give you a parallel has a capacitance of this much. So this is 20 microfarads. How much charge must leak off the plates before the voltage across them reduces by 100 volts? Okay, so this is 20 microfarads.
Did you say that the capacitance has to be the same before and after initial and final?
Yeah, the capacitance doesn't change.
Is that true for all or just this problem?
Yeah, as long as you don't move the plates around, if you don't change the configuration. What the heck? What am I missing? Q. Here's my problem. I know this ratio, except that, and that would be the only unknown, except that I can't pull this out. I substitute this there, 20 microfarad times Vi minus Q. All right, so so
Do we need to write it as Q initial over V initial, or can we just write 20?
no, so what I'm trying to, so here's the equation. Okay, there's the capacitor, that's 20 microfarads, and then this much charge, you reduce the charge by this much and the voltage decreased by 100 volts. So this ratio is also the same. And what we're trying to solve for is this. Okay. And the problem is we only know this ratio. We don't know that individually. So I'm trying to solve for that. Okay. What I did was cross multiply that. Okay. Okay. So
That was my word, by the way.
I know. All right, so here's the argument. So let's say the capacitor was uncharged. And you add this much charge to it, and the voltage increases by 100 volts. Okay. So when you remove that charge, it would decrease by 100 volts. So, and I was just trying to solve it in a different way, but okay. So you add this much charge, and the voltage increases by 100 volts. Okay. So if it's initially charged, you remove that much charge, and the voltage would decrease by that much. So 20 microfarads times 100 volts. And that's 3, that becomes 2 millicoulombs.
It's a lot simpler of a problem. So it's a lot simpler of a way to do it.
Yeah. But I should be able to do it the other way.
You said 100 volts equal to the,
I'm sorry?
you said the 100 volts as V instead of delta V. So that would work.
This one? Oh, so let's say it was initially uncharged, and you add this much charge, and you go from 0 to 100 volts.
So that would work.
Yeah.
From 0.
Yeah. So that was the argument. Yeah, there's something that's bothering me about it, and I can't put my finger, so I'll have to come back to that. Which is Dylan's argument as well. All right, so here's a bank of capacitors, and you want to reduce this to a single capacitor. Okay, so again, you do it stepwise. These two are parallel combinations, so you can reduce that to a single capacitor. These two guys are series, you can reduce that to a single capacitor. So let's do that, okay? Parallel combination is, if effective is C1 plus C2 and so on. And series combination, the formula is 1 over C equal to 1 over C1 plus 1 over C2 and so on. So when you combine these two, it's just 15.75 microfarads. That's what that reduces to. When you combine these two, so let's calculate that. 1 over C is equal to 1 over 5 plus 1 over 3.5. And so 1 over C equal to 5 into 3.5, 3.5 plus 5. So C is 17.5 divided by 8.5. .06 microfarads. And you see, whenever you have a series combination, the effective capacitance is smaller than either one of them, is smaller than the smallest one, and we did get that, okay? So now your circuit reduces to, this is 2.06. This is 8. And then you had 1.5, and this was 15.75. Okay, so now what we'll do is we'll combine these two series, replace that one capacitor, and then those will be in parallel. Okay, so let's combine these two guys. Divided by the sum of those two, that's 17.25. Again, less than either one of them, okay, less than the smallest one. So now our circuit reduces to, so 2.06, 8, and 1.37.
So if they're parallel, are you,
Just adding up.
you're adding them?
Mm-hmm.
And then if they're,
Series, then it's inverse sum.
So if they're parallel, you add them together. If they're like next to each other, like the 5 and the 3.5, like what did you do there? You have to pick one?
That was
Like if they're
series.
perpendicular.
No, these are series. That's a series. That's just a squiggly line telling you what this guy is.
Right, so if they're series, then,
This is series.
oh, it's the inverse, okay, you are just adding the
Mhm.
inverse sum together, okay. Cool. I was overthinking.
So the equivalent capacitance is, that's 10.06, 11.43. Okay. So this mess of capacitors is equivalent to a single capacitor of capacitance 11.43 microfarads. Okay. So, in fact, what you'll end up having to do is, okay, so let's say, so here's a complicated problem, and you might encounter this at one time or another. So you connect it to a battery, let's say 15-volt battery. So this capacitance is equal to that. So here's a 15-volt battery connecting to that. Then charge flows in here. And then you would have to calculate the charge on each one of them. So you would work backwards. This is the charge. That charge distributes onto these three guys. That's a 15-volt battery. And so, so you could connect this, calculate the charge on these guys. This guy, that guy was this guy. So remember, the charge on a series guy is equal. So if this guy was Q, or Q3, this is Q3. You already have the charge on that. And this one was that guy. And that would be Q1 and Q1 and Q1. So that's how you would calculate it. You'd go backwards. All right, so this problem says a 2 microfarad capacitor and a 4 microfarad capacitor are connected in series across a 1,000-volt potential. The charged capacitors are then disconnected from the source and connected to each other with terminals of like signs together. Find the charge on each capacitor and voltage across each capacitor. Okay, so what you have is a 1,000 volts. So this is what we'll be doing. Okay. So when you have a series connection, okay, the charge flowing in here, the electrons flow in here, as many electrons are repelled, and that many electrons come over here. So the charges are equal, okay, when you connect them in series. Okay. And what is this charge equal to? So that charge will be, so you can think of this as a single capacitance, and that charge will equal to that capacitance, single capacitor. Okay, so that'll be equal to the charge on that single capacitor. Okay, so that'll also be Q. So now let's find that single capacitance. So this is a 1.33 microfarad capacitor. Now we can calculate the charge on that. Charge Q is CO times V, which is 1.33 microfarad times 10 to the 3 volts, 1.33 millicoulomb. So now we know the charge on each capacitor, 1.33 millicoulomb. Now what we're going to do is disconnect these guys and connect them in parallel. Okay, so now you connected them in two microfarads, 4 microfarads. And the charges will redistribute. How do they redistribute? When you connect something in parallel, the voltage across this has to be equal to the voltage across this. See, right now the voltages are not the same. So for instance, okay, let me calculate the voltage quickly. Q is, so Q over C, this is the voltage, 1.33 millicoulombs divided by voltage is Q over C, 1.33 millicoulombs. Divided by 2 microfarads, and that is equal to 665 volts. So right now the voltage across this is 665 volts and the voltage across this is 365. This plus this is equal to 1000 volts. These guys got charged, you disconnected them, and the voltages will equalize. Okay, so the charges will redistribute. Now this has become Q1 and Q2. The net charge Q1 plus Q2 should equal 2Q, this Q. Okay? And Q1 over C1, the voltage V1 should equal V2, which is equal to Q2 over C. So now you have two equations and two unknowns. Q1 plus Q2 equal to 2Q, and Q1 over C1 equal to Q. Okay, so now you can calculate these charges. You guys understand what's going on? Okay, so all right, so here is a 1000-volt battery. You have these two capacitors, and these guys will get charged. When you guys have a series connection, then the charges are the same on each capacitor. How do I find the charge? What you do is you reduce that to a single capacitor, find the charge on this guy, and that charge is the same as this charge,
Okay.
which is what we found.
So it's the difference between finding the charge, depending on series and parallel. That's the only difference.
Mhm.
Okay.
So we found the charge. And now you're going to disconnect these guys, which each had that much charge, and connect them in parallel. And the charge will redistribute. Why does it redistribute? Because there the voltage was not the same. The voltage across this was 665 or whatever I showed you. So now the charges will redistribute so that the voltage across them is the same, which is what we are. Okay, so now you have your two equations and two unknowns. Q1 is, C1 is 2 microfarads. Q2 is, this is 4 microfarads. Okay, so Q2 is 2 times Q1. So that's what this equation tells you, okay? And then we'll substitute that there. So Q1 plus 2Q1 equal to 2Q. So Q1 is 2/3 Q. So you see the charge is redistributed. Initially, they had 1.33 millicoulomb each, and charge from here flowed to there. Okay. And Q1 reduced to that, and that increased to that. Okay. A capacitor has a charge of 2.5 microcoulombs when connected to a 6-volt battery. How much energy is stored in this capacitor? So the energy stored in the capacitor is 1/2 CV square. Okay, so 45 microjoules. How much energy is stored in the capacitor in a flash bulb circuit? 20 joules, 20 to 40 joules, so a million times more than that. Suppose you have a 9-volt battery, a 2 microfarad capacitor, and a 7.4 microfarad capacitor. Find the charge and energy stored in the capacitor. If the capacitors are connected to battery in series, do the same for parallel connection. So when do you store more energy? In series connection or parallel connection? Parallel connection. Okay. When you have parallel connection, then you have a greater capacitance. Okay. I'll just do the energy. Okay. All right. We'll do it all. Okay. So. Okay, so whenever you have a series connection, you reduce it to a single capacitor, and C is equal to C1, C2 divided by C1 plus C2. 7.4 into 2 divided by you see, whenever you have a series connection, the equivalent capacitance is less than the smallest one. And the charge will be C times V, which is 1.57 microfarad times 9 volts. 14.2 microcoulombs. Okay, and that's the charge on each one of them. Okay, so find the charge and energy stored if the capacitors are connected to the battery in series. Okay, so that's the charge on each one of them. And now if you want to calculate the energy stored, energy is just, you can calculate using the equivalent capacitance. So the energy stored is 1/1/2 CV squared. So in this series combination, when you connected a 9-volt battery, you stored that much energy. Now let's do the parallel combination. So in the parallel combination, so here's the 9-volt battery, 2 microfarads and 7.4 microfarads. The equivalent circuit is, you're just adding the capacitors, and the energy is 1/2 CV squared. So essentially the difference is this, you see. You see, 1.57 and 9.4. That's about 6 times greater. So with the same 2 capacitors connected in parallel, if you connect them in series, that's how much, 64 microjoules is what you're storing. And with the parallel connection, you're storing 6 times as much, 381 microjoules. Okay. So this says a parallel plate capacitor has a charge of magnitude 9 microcoulombs on each plate and a capacitance of 3 microfarads. When there is air between the plates are separated by 2 millimeters. The plates, with the charge on the plates kept constant, a dielectric K with K equal to kappa equal to 5 is inserted between the plates, completely filling the volume between the plates. What is the potential difference between the plates of the capacitor before and after the dielectric has been inserted? Okay. So the capacitor has a charge. So voltage is Q over C. Okay. So this is C naught, just tells you that it's air in between. Q is 9 microcoulombs and 3 microfarads. So the voltage is, the micros cancel, and that's volts. So this is 3 volts. So with air in between, the voltage is 3 volts. Okay. Now, so this is with air. Now, what we're going to do is introduce the dielectric. And so the new value of the capacitance is just kappa times C naught. So we'll call all of these guys. Okay. So now V is, the charge is the same, divided by the same charge, 5 C naught. This is the original voltage, which is 3 volts. So now so here's what happened. Here was the parallel plate capacitor. You charged it to 3 volts, and then you inserted the dielectric. And when you insert the dielectric, the electric field in the dielectric reduces. And the voltage is E times D, the separation. Okay, when the electric field decreases, the voltage across decreases, and you see the voltage went from 3 volts to 0.6 volts. Okay. So when you introduce a dielectric, the electric field between the plate decreases and the voltage across the plate decreases. What is the electric field at the point midway between the plates before and after the dielectric is inserted? So the voltage across the plates is the electric field times this thing. So V naught is E naught times D. E naught, the field before the dielectric was inserted, was this. 3 volts divided by 2 millimeters. Okay, 1.5 into 10 to the 3 volts. 1500 volts per meter. And after the dielectric is inserted, so what we are seeing is the dielectric constant is 5. Okay, so when you inserted the dielectric constant, the electric field decreases by a factor of 5. Okay. Capacitance increases by a factor of 5. The electric field decreases by a factor of 5.
What did you call that value, the 5, the dielectric constant? Is that what you said?
Yeah, kappa is dielectric constant. And they give you a table for various materials. Mhm. Okay, so what this is a, so you have to notice this is a parallel plate capacitor, and you have inserted it with 2 different dielectrics. And what you want to do is you want to find the effective dielectric constant, and that's what that is. Okay. So how do you look at it? So if you look at this, you can think of this as 2 capacitors connected in parallel. So here's one capacitor with this dielectric, and here's another capacitor with this dielectric, and those 2 are connected in parallel. Okay. All right. And this is an easy configuration. The area of this guy is, if the area of the whole plate is A, the area of this guy is A by 2, and the area of this guy is A by 2, and the distance between them is the same. Okay, so we'll call this C1 and C2. C1 is kappa 1 epsilon naught A by 2 divided by D. C2 is kappa 2 epsilon naught A by 2 divided by D. The net capacitance is just C1 plus C2. Okay, so you see this is the effective dielectric constant. Okay. Here's the capacitance of an air-filled capacitor, and this is the effective dielectric constant. So K effective equal to 1/2 okay. So in general, you know, if you stuff it with all kinds of different dielectrics, okay, you would just take the weighted average of the volume. So the effective dielectric constant will be VI kappa I. So the effective, okay, the fractional volume divided by total volume. Summation over I. Okay. So if you break that into, if you stuff it with different dielectrics, okay, so it'll be 1 over V. Okay, that's how it would turn out. All right, guys, that finishes the problem.